An object has a velocity u at time t equals 0. The acceleration of the object varies with time as a of t equals kt. What is the velocity of the object at time ta? We'll look at two different solutions for this problem, one using calculus and the other one without calculus. We know that acceleration is the rate of change of velocity, and so it's dv by dt, and it is given to be k times t. Now we will write this conveniently as dv equals k times t dt and integrate both the sides of this equation. On the left hand side, we will use the limits of u and v because u is the initial velocity and v is what we are trying to find. And on the right hand side, we will use the limits of 0 and ta. On doing this integration, we will find that v equals kta square by 2 plus u. However, this problem does not really need any calculus. We have a as a function of t. It's given to be a equals kt. So whenever you have any equation that represents the relationship between two quantities, you first try to figure out the curve that the equation represents. In this case, it's quite straightforward. We know that this is going to be a straight line because the equation of a straight line is y equals mx plus c. And this is of that form, right? A equals kt plus 0. So here the slope is k and the y-intercept is 0. So this is the kind of curve this equation would represent. Now in a velocity time graph, we know that the area between the curve and the x-axis represents the displacement during any interval of time. The area above the x-axis represents a positive displacement and the one below represents a negative displacement. And displacement is basically the change in position. We can carry forward the same thought to the acceleration time graph too. In an acceleration time graph, the area between the curve and the x-axis represents the change in velocity, whereas earlier it was the change in position in the velocity time graph. Here it is the change in velocity. We'll see why. Consider any small strip, a rectangle, between the curve and the x-axis. Assume this strip to be so thin that in this duration of time, delta t, the acceleration remains a constant. So the area of this rectangle would be delta t times a, right? So delta a, which is the area of this small rectangle, equals a times delta t. But a is the rate of change of velocity, which is delta v by delta t, and so the area of this rectangle is basically delta v, the change in velocity. So if you consider any interval of time in this graph, the area between the curve and the x-axis would be the sum of all the changes in velocities, right? So you could draw infinite number of these rectangles, and the area of each rectangle would represent the change in velocity during that duration of time. And so if you add up all the areas, you basically get the total change in velocity between those two time instances. And so that's why in the acceleration time graph, the area between the curve and the x-axis represents the change in velocity. In our problem, the curve is a straight line, and so the area between the curve and the x-axis between time instances t equals 0 and t equals ta would represent the change in velocity during this time interval. Now this is a triangle, and so we can easily find its area. At time ta, the acceleration is going to be kta because a equals kt. So we know the height as well as the base, and so the area of this triangle is half times ta times kta, which is kta square by 2. Now this represents the change in velocity, but at time t equals 0 the velocity was u, and so at time t equals ta the velocity would be u plus the area, that is kta square by 2, kta square by 2 plus u. That was easy, right?